Hey everybody, Dr. A here, and in this video, my daughter and I are going to be providing some background information on couple moments. Now, you might notice in this video and some of my other videos, I reference a textbook. That's going to be the Hibbler Statics textbook. That is a great textbook for all of your statics knowledge. So I suggest if you have a copy of that, follow along in that book as well. And remember, before we get started, to hit like and subscribe, okay? We ready? Okay, we're ready. Let's get started.
In this video, we're going to be getting into our next section, which is 4.6, entitled Moment of a Couple. Now, we often call this, so I'm going to say AKA, we often call this a couple moment. So if you look back in your notes and some previous videos, you'll see that we had several different types of moments that we briefly summarized. We had torque moment, bending moment, couple moment, and something else called moment of inertia. We'll get to that in some later videos. But right now we're talking about what's called a couple moment. Now, a couple moment is still a tendency of rotation, but it has kind of a special case. All right, so let's talk about what that is. So when two parallel forces with the same magnitude but opposite directions act on a system and are separated by a perpendicular distance, a couple moment is generated. So again, in this case, you have two forces with the same magnitude, but they're pointing in opposite directions, and they are separated by some perpendicular distance between the two forces. You get what's called a couple moment. So it's very easy to see that in two dimensions. If you have a force here, okay, and then parallel to that, you have the same magnitude force, and they are separated by this perpendicular distance right here. Let's call it D. Then we have a couple moment. By the way, all these are vectors. Let's be proper here, put vector hats there. You have a couple moment, which is still a vector, that is equal to D times F, okay? Now, if you want to put this in vector form, it is still a cross product, D cross F or R cross F. Okay, in scalar form, of course, it's just D times F. Okay, so in two dimensions, we definitely use the scalar form most of the time, pretty much all the time. In three dimensions, we use the Cartesian vector notation, and that's pretty much it. So let's talk a little bit more about how this works. So a couple moment is known as a, quote, free vector. And the reason why is because it only depends on the position vector between the parallel forces. Okay, so let's maybe look at a 3D view of this. Okay, so let's say that we have some point down here. Let's call it the origin. All right, and again, I'm going to try to draw this in 3D. Let's say I have a force vector here, and I have a parallel force vector here with the same magnitude. Okay, and let's say that I have a position vector from this point of origin to some point on one of these forces, and I call that RA. And let's say I have another position vector from the origin to a point on the other parallel force. And let's say I call this RB, okay? So that's what we have at first. So at first we may try to use some of the moments, right? So we could end up saying a couple moment, a vectorized couple moment is RA cross F plus vector RB cross negative F. Okay, where am I getting this from? Well, to kind of illustrate how this works, I'm going to say RA cross F. All right, so maybe I should put little arrowheads here. All right, RA cross F. So that's going to give me the moment about point O due to F acting through RA. And then I'm going to say plus RB cross negative F. The negative indicates that this vector F is pointing in the opposite direction of the other one. And again, this is giving me the Cartesian vector notation of the moment generated by F rotating through RB. All right. So, and again, the negative is just indicating that this vector force F is pointing in the opposite direction. So I can do a little bit of algebra here, and I can do some factoring and gathering of terms, and I can end up saying that this is RA minus RB cross F. Okay. And what next? Well, you may be like, oh, I'm kind of stuck here, but look at the relative distance between these two corresponding points between the parallel force vectors F. So if I call this position vector, oops, didn't mean to scroll there. If I call this position vector just regular R, okay, then what do I have here? I can write RA equals RB plus R. Okay, that's just a vector sum. Again, RA, if you did, oh man, I didn't mean to scroll again. If you do RB plus R, then you get RA by vector sum. Okay, so doing a little rearranging here, we can say that R equals RA minus RB, and then we can say thus couple moment C equals R cross F. So this is just like a little proof. I'm going to call that little proof that the couple moment generated by two parallel forces, it's really only dependent on the position vector between the forces and not these other position vectors. So again, that's why we call it a free vector, okay? So the cool thing about this is because of this property, we can sum moments about any arbitrary point when these moments are couple moments. And we'll kind of see this illustrated in an example soon. Now, what happens if you have several couple moments acting in a system? So let's write that down. When several couple moments are present, what do we have? We would have a resultant couple moment equals the summation of R cross F. We could say sub I, as I goes from 1 to n, where n equals the number of couple moments on the system. So again, we just add up all of the couple moments together if you have multiple of them acting in a system. So that's the background of it. And in the next couple of videos, we're going to see some examples of this.